So 2.4 is on continuity. Okay. Continuity is very important for a number of reasons. If you're, okay, so for one thing, if you're studying limits, then continuity is a big topic in context of limits. But then we go to do calculus, derivatives and integrals, the other chapters we're going to cover. Continuity is really important because a lot of the theorems only work on functions that are continuous. So you need to check for continuity before you can even try to apply the theorem. And in a very short, a very well, a very brief but perhaps somewhat simplistic way to describe what continuity is, and we'll go into the details, of course, but the concise and maybe missing some of the details is to say that a continuous function is one that is one smooth curve that you can draw. Oops, let me get the pen out. One smooth curve that you can draw. That's not technically correct, but that's one way of thinking about it, that you can draw it in one motion without lifting your pen or pencil. But of course, there's more detail than that. So let's talk first about continuity at a point. Okay. So basically, continuity at a point means that there are three things that happen. So one, and basically you have to have some function and some value. So continuity point given function f of x and a number a in the real numbers. Okay. One, you need for f of a to exist. Okay, the function must be defined there. So basically, you need a to be in the domain of the function. Two, you need the limit as x goes to a of f of x to exist. Okay. And in this context specifically, you need to have a numerical limit, because to have continuity, you're basically, since infinity is not a number, f of a cannot be infinity, right? So if your limit is infinity, well, then the next item is not going to be met. So ultimately, you need the limit to be a number as well. So step 3, or part 3, the limit and the function need to agree. You need for limit as x goes to a of f of x equals f of a. Okay. So these three conditions must hold. Oops, sorry, I hit the mic there. These three conditions must hold in order for you to have continuity at a point. Okay, so we'll look at a few examples. Now, there's another thing called discontinuity, and different books handle it different ways. In some books, a function is discontinuous only if the first one is met, but these two are not met. The function has to exist to be discontinuous. Okay. So this textbook uses the terminology slightly differently. This book says that a function is discontinuous at a point if it fails to be continuous at a. In the web work assignments, I'm going to have to check whether that definition is held the same way. Basically, the textbook that used to be used for this course defined it the way I just described, where point 1 has to be met, and then points 2 and 3 have to fail, or at least one of them has to fail. Then you get discontinuity. But this book, if you just look at the definition in the textbook, it says, literally, I'm reading the textbook here, a function is discontinuous at a point if it fails to be continuous at a. That is not how certain other books define things. As I said before, different books will define things different ways because different authors are presenting things slightly differently. And you have two books that are totally internally consistent. There's nothing wrong with them, but they have slightly different definitions and they go about things slightly differently. They reach the same conclusions basically, but they're just different. So I will have to double check in the webwork assignment which one it takes for section 2.4. I will double check that, and when I make the assignment available, I'll double check that, and I'll make a post in Blackboard saying, hey, this is the clarification so that you don't get confused. Because some of the problems in Blackboard will ask you to check these points, determine if there's a discontinuity or not, and then what kind of discontinuity. And so knowing that thing I'm just describing is very important. We will go with what the book says for now, because the book says that discontinuous just means that any of these fail. Okay, but if the webwork assignment doesn't treat it that way, then I will clarify this. Okay, I'm used to saying it the way I described first, but we'll go with what the book says because I don't want to deviate from the book too much. Okay, so let's look at a few examples of. You go find it in my lecture notes here. Find them rather. Okay, so yeah, let's just do a few examples. So let's say this. I also don't think the textbook distinguishes one-sided continuity from two-sided continuity. I think the textbook, yeah, it doesn't do that. Okay, that's fine. So let's say I had a graph like this. Okay, so let's say I have an asymptote. Got something like this. Something like this. Something like that. And let's say something like that. That probably captures several of the different types of discontinuities. Okay. So actually, there's one more. There's one more. I'll talk about that one separately. That one doesn't come up as much. There's 3 primary discontinuity types. So if we call this A, call this one B, call this one C, and call this one D, right? So at A, this is what's called an infinite discontinuity. The function is not defined there. There's a vertical asymptote. So the left limit is positive infinity, and the right limit is positive infinity. Okay, so item 1 doesn't meet, or is not met rather, because f of A isn't defined. There's an asymptote. So item 1 fails. Okay, so infinite discontinuity. So number 1 fails. Okay, let's do this. Put that there. Okay, so for B, if you look at f of B, well, f of B is whatever that y coordinate is. There's a point there, there's a dot, so the function is defined. So item 1 is met. If you look at the limit from the left, you get, like, I don't know, maybe that's 2 or something. Let's just say it's 2. If you look at the limit from the right, that's maybe like 0.5, I guess. So the left limit and the right limit disagree. So we don't get a two-sided limit. So item 2 fails. This is called a jump discontinuity. And I'll abbreviate discontinuity as just disc. Jump discontinuity. 2 fails. Okay. So from a graph, it's usually relatively easy. And one way to say it is if you were a person walking along here, you'd have to jump to get up to the next part, or you'd have to, if you're on the other side, you'd have to jump to get down to the other side, right? It's jump discontinuity, the graph jumps. Okay, so at C, well, vertically, I don't see a dot anywhere. The function appears not to be defined. So actually, I am missing one type. So let's do this. Let's do this. Add that in there. Okay. Call that E. Okay, so this one, there's a hole in the graph. There's no point there. So this is called a removable discontinuity. And why is it called? Well, I'll talk about why it's called that in a second. item 1 fails in this case. So item 1 failing can be the result of an infinite discontinuity or a removable discontinuity. It depends on the graph. So why is this called removable? Well, it's called removable because you could just fill in the gap and go, oh, no. F of C is 2 or 2.2 or whatever it is. You could fill in the gap by just saying, oh, no, the function's defined there. No problem. And we'll probably do an example of that. So you can see, I say probably, I think we're definitely going to do an example of that so you can see what I mean by filling in the gap. And I'm going to put some divider lines here as well. Okay. All right, so item D. Well, looking at this one, the function is defined. There's a point there at D. The left limit and the right limit connect. So they're like 3 or something. They're both equal to 3, I suppose. So the two-side limit is 3. The function value is 3. That means they agree. All 3 points check out. This is continuous here. So all 3 items are met. Okay, so if all 3, the function exists, the two-side limit exists, and they agree, those 3 things, then you have continuity at a point. Okay. This last one, and this is not the fourth, the other type I was thinking about. There's another type, but I don't have room for it on this graph, so I'll handle it separately. This one, if we zoom in, well, the function is defined, right? Especially if I move it over slightly. The function is defined, right? F of E is like 2.5 or something. And then if you look at the left limit and the right limit, they connect. So the two-side limit is like 1.8 or something, ballpark. But the two values disagree. They're not the same value. The function value and the limit value are different. So item 3 fails in this case. This one is also called a removable discontinuity. Because you could say, no, don't use that guy. Just fill in the gap. Say, no, actually we mean f of e is supposed to be 1.8. You can do that if you want. If it's useful, you can modify a function. If your function is not behaving the way you want, you can modify it so that it does. Okay. So here, item 3 fails. But removable basically means that you can repair the graph and make it continuous at that point. Infinite, you can't. A jump, you can't. And then other times the graph is just continuous. So basically, at all of these points along the graph that we weren't pointing out, all of these, the function is continuous. If you check the function is defined, look at the left limit, look at the right limit. So anytime you have what's called a smooth curve, like this entire section here, oops, wrong marker. This entire section here is just drawn as a smooth curve. I didn't have to put like an open circle or a closed circle or put an asymptote or any of that. It's a smooth curve. So another term that's commonly used for continuous functions is that they're smooth. Now, smooth is actually a technical term that means something a little bit more complicated, which maybe we'll talk about later. That might come up later. I think it will. We don't have to use that term, but we probably will use the term. So you could just say it's a smooth curve, although that's a technical term that's usually reserved for something else. Anyway, so that's just visually what continuity is about.